Hello and welcome. What do you get when you cross an elephant with Darth Vader? An elevator. Don't tell him I said that. In this video, we're going to look at finding the area of a region in a polar coordinate system. Let's get started. What we're looking at is figure 1 from the notes, and this is an interactive version of it, so we're going to get a chance to play around with it. Now the idea is, if we're trying to find an area given a polar equation, we're not going to be thinking about the area from the polar curve to the x-axis. Rather, we're going to be finding the area from the polar curve to the origin. So that's what this picture is showing. It's showing the area, or it's showing a region from the polar curve to the origin. Now to find that area, we're going to break up the region into break up the interval of theta values. So this line here represents some theta value. It's theta equals 15 degrees, and then the end interval is theta equals 75 degrees. So we're only looking at the polar curve from 15 degrees to 75 degrees. Most of the time we'll be working in radians, but just for the sake of this example, we're in degrees. So we're trying to find the area of the region from this polar curve to the origin. And one way of starting about that is to take our interval of theta goes from 15 to 75, and cut it up into a number of subintervals. So take 75 divided by 75 minus 15 divided by 4, and that'll give you the angle for each of these subintervals. So the interval and the subintervals are in theta. They're not along the x-axis anymore. They're in theta. Now for each of those subintervals, we can use a sector to approximate the area of between the curve and the origin on that little subinterval. So on the first subinterval here, we can make a sector, and to get the sector, we can take any theta value inside of that subinterval, plug it into the polar curve to get the r value. So here this is r equals f of theta, so we can plug in a theta value to get the r value, which is like the distance from the origin out to that point. And that can give us the radius of the sector that we're going to use for the approximation. We can do the same thing for the next subinterval, and the next one, and the next one. Plugging in the theta values, and here I'm just using the middle theta values, kind of like the midpoint, to figure out the radius of this approximating sector. Now, this is not going to give us the true area from the polar curve to the origin, because you can see there's a little bit of area that we haven't counted here. There's a little bit of area here that we've overcounted. There's a little bit in each of these subintervals that we're not counting, and a little bit that we're counting too much. But it gives us at least an approximation that can get better the more subintervals we use. So here's 5 subintervals. 6 subintervals, 7 subintervals, 8, 9, 10. So this is looking more and more like figure 2 in the notes. The more subintervals you use, the tighter the sectors are going to be to the true area of the region. So if we can figure out all of the areas of those little sectors and add them all up and start using more and more of them, then we're going to approach the true area between the polar curve and the origin. Let me back up here. See now if you used one sector, that would be not a very good approximation, but then 2 sectors gets better, 3 sectors, and 4 sectors. I'm just having fun here. Okay, so let's turn to the notes to work out the details. Now our first job will be to find the area of a sector, find the formula for the area of a sector. And I've written some things in the notes to help out with that. So suppose we're trying to figure out the area of a quarter of the circle. Well, to find that out, you would take 1/4 of the area of the whole circle, right? You take 1/4 times the area of the circle. Now one way of figuring that out based on the angle that the sector makes would be take the angle, and here I'm again just in degrees for the moment. Like let's say we have 90 degrees. That would be a quarter of the circle, right? That sector would be a quarter of the circle. We could take that 90, divide it by the total angle all the way around, which would be 360 degrees. That would be for the full circle. and divide them. 90 divided by 360 would give us 1/4. So 90 degrees is a quarter of 360 degrees. So the area will be a quarter of the full area. You could do the same thing for half the circle, right? Half the circle, you'd have to go 180 degrees around, and the area of that sector that's made will be half the area of the full circle. The way we can get the half is by taking the angle and dividing it by 360. So in general, that's true. If you have the angle of a sector, theta, and you want to find out what fraction of the full circle is that sector, you can take the theta, divide it by 360 degrees, and that'll give you the fraction that the sector represents of the full circle. Now, most of the time we're not going to be using degrees, we're going to be using radians. So the equivalent of 360 degrees in radians is 2 pi. So theta over 2 pi will represent the fraction of the circle, or fraction of the full circle that the sector takes up. So if we multiply that fraction by the total area of the circle, we're going to get the area of just that sector with an angle of theta. Now if we simplify this, a couple of pi's cancel, we can write the over 2 as a half, and we get 1/2 r squared theta. This is the area of a sector. Now in figure 1, let's try to pull some details out. We're going to have to name some things, and the first thing we're going to name is the start and the end of our interval. We're going to call the start of our interval theta equals, theta equals infinity. That's no good. Theta equals alpha. Infinity is like an alpha gone wrong. So theta equals alpha, and then theta equals beta will be our end interval. Usually you use Greek letters to talk about angles. It's just a thing. Now we're going to take that interval of theta values and cut it up into subintervals. The width of each subinterval we're going to call delta theta. That's reminiscent of our delta x's when our intervals were in x. So each of these subintervals has a width of delta theta. That's the angle that each of those subintervals makes. Now, what we're going to do is then, inside of the subinterval, pick some kind of theta value inside that subinterval, plug it into the curve, and let me actually just mention the curve here. So this is r equals f of theta. We'll call it r equals f of theta. Remember that to write a polar function, usually we try to solve for r, so solve for r as a function of theta. That way it'll be a function in a polar kind of sense. So now we're going to take, again, a theta value inside the first subinterval, plug it into this polar function, and get the radius at that theta value. So we can label it like this. This is R1, we'll call it. Make that a little bit more clear. This is R1. That's what you get when you plug in theta sub 1, that first theta value, into the function. And then you'll have an R2, going with the Star Wars jokes, and then an R3 and an R4. So the last one will be R4. R2, where are you? I'm right here. There. I'm making these videos too late at night. So, so this gives us something to work with when we're trying to figure out the algebra that's going on. So down here it says for a curve r equals f of theta, the area of each approximating sector is going to be, well, a sub k. K is going to represent the index, so this is k equals 1, k equals 2, k equals 3, and k equals 4, the 4 sectors. So the area of that first sector will be 1/2 r sub k, or r sub 1 squared, and then delta theta. So in general, it'll be 1/2 r sub k squared delta theta. That's the area of each of these sectors. So we can get our Riemann sums that approximate the area of the region by adding up all of those little areas of the sectors, which look like this. Then take the limit as the number of subintervals goes to infinity, and we turn that into the integral from the start of our interval, which is theta equals alpha, to theta equals beta, of 1/2, and then the r sub k's, just like the x sub I is turned into x, the r sub k's here are turning into r, and then the delta theta is going to turn into the d theta. That's just by the definition of the integral. So this is going to give us the true area between the polar curve and the origin. And that's summarized in the box. The area of the region between the origin and the polar curve, r equals f of theta, from alpha to beta, is going to be given by this integral, the integral of 1/2 r squared d theta. So when you're looking at this formula here, I'll put in quotes, you can see that it's really just the formula for the area of a sector. It's 1/2 r squared times theta. But in this case, the thetas are just the with the angles of each of the subintervals. Now, one note again is that when you're looking for this area, you're looking not for the area between the curve and the x-axis. That's no longer the case in polar. You're looking for the area between the curve and the origin. That's the key difference that you really have to wrap your mind around to understand this section and to understand this formula as well. The other note is that as you go from theta equals alpha to theta equals beta, you've got to make sure that you're traversing the curve exactly once. If you go around the circle many times, you're going to be counting more areas of sectors than you want. You're going to be double counting the area of the region, or triple counting, or more. So you want to make sure that you're traversing the curve exactly once. Let's check out example 1, which says find the area of the region in the plane enclosed by the cardioid r equals 2 times open paren 1 plus cosine theta close paren. So in figure 3, it graphs that cardioid. Remember that the cardioids with cosine theta are going to be oriented along the x-axis. So it's going to be oriented along the x-axis with symmetry about the x-axis. And in this case, we can think if theta equals 0, that's the biggest cosine ever gets. Cosine gets to be 1. 1 plus 1 is 2, times 2 gives you an r value of 4. So you're going to start out here at an r value of 4. You can actually, if you know that it's going to be a cardioid, you can just plot the key points to get a quick sketch of that cardioid. Once you know the form of the cardioid, just plug in a few of the key points, like theta equals 0, theta equals pi over 2, theta equals pi, and theta equals 3 pi over 2. Those ones will give you at least the points that you can draw your quick sketch of a cardioid through, in case you don't have a graph of it already, like figure 3. When we look at this, if we want to find the area of this region that's enclosed by the cardioid, in other words, this area here, and one way to help you remind yourself that the area is between the origin and the polar curve is maybe not to shade it like this, like I just did, but you can think about it as shading it like this, from the origin out to the polar curve. That will get you in the habit of thinking that your area is, again, calculated from the origin out to the polar curve. Now it's still the same region, but we're just thinking about the area in a different way, about computing the area in a different way. So if we're going to figure out the area of this region, well, we're going to have to go all the way around the cardioid. We're going to go from theta equals 0 to pi over 2 to pi to 3 pi over 2, and then back to 2 pi. We're going to go all the way around the cardioid, 0 to 2 pi. So that's our interval. Then we're going to write 1/2 times r squared, where r is 2 times 1 plus cosine theta in paren. So that's your r squared, and then we just have d theta. So not too bad, actually, setting up the integral. I'm just going to take a couple of steps here to remind you how you can evaluate one of these integrals. For one thing, if you look at the 2 squared, that's going to give you 4, times 1/2 gives you 2. So you have the integral from 0 to 2 pi. You can put the 2 out here if you like. And then if you square the 1 plus cosine theta, you're going to get 1 plus 2 cosine theta plus cosine squared theta, d theta. Now the 1 you can handle, the 2 cosine theta you can handle. The cosine squared you want to lower the power of before you integrate. So 1 plus 2 cosine theta, and then you have plus 1 plus cosine 2 theta over 2, using the power lowering formula. And then from here you can take it away, and you end up getting something like 6 pi. So I encourage you to try that integral just to keep your integration skills fresh, and make sure that you get 6 pi at the end. Thanks so much for watching this video, and see you in the next part.